Hello everyone, and welcome to today's presentation on specialized joining principles, equipment, and applications. I'm excited to have you here as we explore Module 4, USW and Brazing, part of the AUT 434 Advanced Metal Joining Techniques course. Over the next few slides, we'll cover the key principles, the equipment involved, and various applications of these advanced joining methods. Let's get started. Let's take a look at the overview of the modules we'll be discussing today. First, we have capillary action-based liquid-solid joining, which involves using low-melt filler metals. This process leverages capillary forces to create strong, precise joints, especially useful when working with small or delicate parts. Next, we'll explore brazing processes, a classic method that involves heating and melting a filler metal to bond two surfaces together, often used for its durability and reliability in various industrial applications. Finally, we'll cover ultrasonic welding, a technique that applies high-frequency vibrations to join materials, particularly effective for delicate components that require precise, solid-state bonding without the need for heat. Each of these methods connects to our overall theme of advanced, efficient joining techniques, tailored to different material types and application needs. In ultrasonic welding, or USW, the principle is centered around local heat generation caused by surface friction. This friction effectively breaks up surface oxides and contaminants, which are often barriers to bonding. Once these are disrupted, atoms from the surfaces can diffuse across the interface more easily, leading to a strong metallurgical bond. Importantly, this process happens without melting the materials, which helps preserve the integrity of the components. Now, when we talk about bond formation in USW, it's a solid-state process. That means there's no melting involved, just high-frequency vibrations, typically between 20 and 40 kilohertz, applied under moderate pressure. These vibrations cause the surfaces to rub against each other at a microscopic level, promoting diffusion and creating a reliable, durable bond. The key to understanding the mechanism here is recognizing how these vibrations generate enough heat locally to clean the surfaces and enable atomic diffusion. This process results in a robust metallurgical connection, all without reaching the melting point of the materials. It's a clever way to join components efficiently, especially when maintaining material properties is crucial. Let's take a closer look at the USW equipment and variables. The key variables we need to control are amplitude, clamping force, and weld time. These are essential because they directly impact the quality of the weld joint. If any of these are off, the weld might be weak or inconsistent. Now, moving on to the equipment itself. The sonotrode, or horn, is responsible for delivering vibrations directly to the workpieces. Think of it as the tool that applies the energy needed for ultrasonic welding. And behind the scenes, we have the transducer. Its job is to convert electrical energy into mechanical vibration. This conversion is critical because it provides the vibrations that the sonotrode then transmits to the materials. All these components and variables work together to ensure we achieve a strong, reliable weld. By understanding and controlling these elements, we can optimize the process and maintain high-quality standards throughout production. Now, let's take a closer look at the different types of ultrasonic welds. First, we have specialized circular welds that are used primarily for sealing tubular or cylindrical components. These are essential in many industries where a strong, sealed connection around a round surface is required. Next, we encounter ring welds. These are created by moving the sonotrode along a linear path, which allows us to produce continuous seams. This method is particularly useful when we need a seamless, durable joint along a length of material. Then there are line welds, which are used for localized bonding between flat, overlapping sheets. These are especially ideal in electronics, such as for attaching connectors where precision and strength are key. Each of these weld types plays a unique role in ultrasonic welding, helping us address different design needs and material challenges. Understanding these options allows us to choose the right method for each specific application, ensuring quality and efficiency throughout the manufacturing process. Let's take a closer look at the advantages and limitations of USW, or ultrasonic welding. One of the key advantages is that it can produce possible surface marking from the horn, which is something to keep in mind depending on the application. It also requires overlap, so typically we're talking about lap joints only, which can be a limitation depending on the design. The initial equipment cost can be quite high, which might be a barrier for some operations. However, USW is excellent for thin materials like foils or sheets, making it very suitable for lightweight or delicate components. One of the biggest benefits is the very small heat-affected zone, or HAZ, meaning less thermal distortion and better preservation of material properties. Plus, it offers extremely fast cycle times, often in less than a second, which boosts productivity significantly. Another important point is that it doesn't require filler metal or flux, simplifying the process and reducing potential contamination. Additionally, USW can join dissimilar metals, such as aluminum to copper, broadening its application scope. Now, looking at the limitations, aside from the equipment costs and the surface marking, it's important to remember that this process is limited to relatively thin materials. It's not suitable for thicker parts. Also, since it requires overlap, it's not as flexible for all joint types. Overall, USW offers many advantages, especially in speed and material versatility, but it's essential to consider these limitations when evaluating it for your specific manufacturing needs. Now, let's move on to the second part of our discussion, brazing. As we explore this method, you'll see how it aligns with the theme of precision joining through capillary action. Brazing is a process that involves joining two metals by melting a filler metal into the joint, which bonds by capillary action. The key here is that the filler metal flows into the small gaps between the parts, creating a strong, reliable joint. This process is especially useful when we need precise, high-quality connections without melting the base materials themselves. Throughout this presentation, you'll notice that brazing exemplifies how capillary action can be harnessed to achieve secure and accurate joins, fitting perfectly into our broader discussion on advanced joining techniques. Let's take a closer look at the principle of brazing. The key idea here is how the liquid filler metal is drawn into the joint. This happens through capillary action, which is a fascinating physical phenomenon. When the filler metal is heated above 450 degrees C, but still below the melting point of the base metals, it becomes liquid and is able to flow into very narrow gaps, typically between 0.05 and 0.2 millimeters. The narrow clearance is essential because it allows the liquid filler to be drawn in effectively. As the filler metal enters the joint, it wets the solid surfaces of the metals being joined. This wetting is crucial because it ensures a strong, continuous bond once cooled. The process relies heavily on the capillary action, which is driven by surface tension and adhesion forces. Connecting this back to the overall theme, understanding how capillary action works is fundamental in brazing, because it explains why the process can produce strong, reliable joints even in very small clearances. It's this precise flow of filler metal that makes brazing an efficient and effective method for joining metals. Let's take a closer look at some of the key brazing processes. First, we have vacuum brazing. This method offers high purity because it takes place in a vacuum environment, which means no flux is needed. It's especially critical in aerospace applications where cleanliness and strength are paramount. Then, there's induction brazing, which uses magnetic fields to generate rapid, localized heating. This process is highly efficient and precise, making it ideal for complex or sensitive components. Moving on, we combine vacuum and induction methods to leverage their respective advantages for specific applications. Now, switching gears to more manual and flexible techniques, we have the torch brazing process. This involves using a gas flame, which allows for on-the-spot repairs and small-scale work. It's versatile and handy in many situations. Lastly, we have furnace brazing, which is suited for bulk processing. This method involves heating parts in a controlled atmosphere, ensuring uniformity and quality across larger quantities. Together, these processes demonstrate the range of options available in brazing, each suited to different needs. Whether precision, speed, or versatility, highlighting how these techniques fit into the broader manufacturing landscape. Let's take a closer look at the benefits and constraints of brazing. First, when it comes to joint strength, brazing can actually exceed the strength of the base metal itself, which is a significant advantage. However, it's important to keep in mind that this strength heavily depends on the proper clearance between the parts, so precision is key. Moving on to complexity, brazing is quite versatile because it allows us to join complex, multi-part assemblies that might be difficult to weld or fasten otherwise. On the flip side, this process requires careful pre-cleaning of the parts to ensure a good bond, which can add to the preparation time. Regarding aesthetics, brazing provides neat, clean joints with minimal finishing required, making the final product look professional and polished. But there's a caveat: flux residue can be left behind, and it must be thoroughly removed to maintain the appearance and prevent corrosion. Finally, on materials, brazing is quite flexible because it can bond ceramics to metals, expanding the range of applications. Yet, selecting the right filler metal is crucial, as compatibility plays a vital role in achieving a successful, durable joint. Overall, brazing offers many strengths, especially in joining different materials and complex assemblies, but it also requires attention to detail and proper process control to overcome its limitations. Now, let's take a closer look at some of the key industrial applications of our technology. First up, brazing is a critical process in the creation of fine jewelry. It allows for precise, durable joins that are essential for high-quality pieces. Moving on, brazing also plays a vital role in HVAC components, where reliable and efficient connections are crucial for system performance. Another important application is the USW, or ultrasonic welding, used extensively in battery tab assembly. This process ensures strong, consistent bonds in battery manufacturing, which is increasingly important as we see the rise of electric vehicles and energy storage solutions. Overall, these applications highlight how our technology supports diverse industries, helping them improve quality, efficiency, and reliability. It's a great example of how advanced manufacturing techniques are shaping the future across different sectors. Thank you for your attention. I really appreciate you taking the time to learn about advanced metal joining techniques today. If you have any questions or need further clarification, now is the perfect opportunity to ask. Remember, the key points we discussed, such as the importance of proper process control, understanding different joining methods, and considering material compatibility, are crucial for successful applications in real-world manufacturing. I encourage you to connect these concepts with your own projects and research. Again, thank you for your engagement, and I look forward to your questions. Now, let's take a moment to acknowledge the sources of the images we've seen throughout this presentation. First, we have an image from lafaledusud.com, which provides valuable visual context. Then, there's a picture from kindletech.com, showcasing advanced technological applications. Moving on, we see an image from mtweldultrasonic.com, illustrating ultrasonic welding equipment in action. Next, we have a photo from Harris Products Group.com, highlighting industrial tools used in manufacturing processes. Finally, an image from Ultrasonic Solutions.in demonstrates the practical implementation of ultrasonic technology. These sources help us understand the diverse applications and visual aspects of the technologies we've discussed. Recognizing where these images come from also emphasizes the importance of credible and detailed visuals in explaining complex concepts. Overall, these visuals reinforce the key points we've covered: how ultrasonic technology plays a crucial role across various industries, and how important it is to reference accurate sources for technical information.